So we're gonna start. So today it's a pleasure to introduce Professor Nina Hatch, who specializes in galaxy evolution in clusters, particularly looking at the intracluster light and the formation of high redshift protoclusters. She completed her PhD at the University of Cambridge in 2006 on ionized and molecular gas in brightest cluster galaxies. Then she moved for a first postdoc at the University of Leiden, which she completed in 2009. And then she moved to Nottingham, where she remains now as a professor in astronomy. Nina was recently awarded a £1 million Research Leadership Award by the Leverhulme Trust in the UK to research dark matter with intracluster light using Euclid. Nina, thank you so much for accepting our invitation and for rescheduling because of our flood issue. You may start in just a moment. We have questions that can be asked through this QR code. So please scan and write it while you listen to the talk. Nina, you may start when you're ready. The floor is yours.
Okay, thanks very much. And interrupt me if you can't hear me or something goes wrong. So thanks for that introduction. I'm going to be talking to you about a paper that we wrote recently, which is about intracluster light that is seen by Euclid in this particular cluster that you can see in front of you, which is the Perseus cluster of galaxies. But before I go on to that, I'm just going to spend a few minutes talking about what intracluster light is. So intracluster light is generally a very low surface brightness light, and it's light from stars that are the diffuse remnants, I'll move that out the way, the diffuse remnants of tidal stripping and mergers. We've known this for quite a long time. It's almost 100 years that we've actually known that intracluster light exists. It was first seen in the nearby Coma cluster. But the reason why we really haven't quantified it until recently is due to the immense difficulties in observing it. It's so faint that it's actually 1,000 times fainter than the night sky, which means we need to use very accurate and precise methods to subtract off the night sky brightness to see the light that's behind it. So although it is really faint, that doesn't mean that it's not actually significant. So the movie which is showing on the bottom right, that shows you all of the stars that are stripping in the tidal streams. But the picture to the left, I wonder actually, can you see my pointer or not?
Yes.
Oh, excellent. So the image to the left is actually a real image of the Virgo cluster. And what I'm going to do is I'm going to mask out the high surface brightness regions here and here, and so allowing you to see the intracluster light that exists beyond those high surface brightness regions. So this type of image you wouldn't be able to see unless you imaged very deeply the same patch of sky again and again and again. And this is what Chris Myhos did for the Virgo cluster. And you can see these sort of stream features, which are very reminiscent of what you can see in the simulations, suggesting that these processes do really happen. Now, the amount of stars in this region between the galaxies is actually quite significant. So it's somewhere between 15 to 60% of all of the stellar mass that exists within a cluster actually exists between the galaxies rather than within the galaxies. But this number depends very much on a definition, and that's because the definition is really hard to pin down. How do you determine whether a particular star is within a galaxy or within or outside the galaxy and in the cluster is difficult to do. So we study intracluster light for a number of reasons. one of the reasons why it's come back into fashion at the moment is because of this amazing paper by Mireia Montes, which was in 2019, which showed us that intracluster light is a very good tracer of the dark matter halo of clusters. And I'll just walk you through these images. So these are all images of this particular cluster, which is one of the Hubble Frontier Fields clusters. So it was observed for many days with Hubble. And in this first image, you can see the contours of the intracluster light. And in the next image, you can see the contours of the total mass in the cluster. Now, these contours were constructed from the shear map constructed from the gravitational lensing signal of the background galaxies. And what you should be able to see is that the contours of the intracluster light match very well with the contours of the total mass. And in the last image, you can see the green contour of the intracluster light and also the total mass, and they align almost perfectly. They don't align very well with this red contour here, and this red contour comes from the X-ray emission from the intracluster medium. So these are the baryons in the gas of the cluster, and this is the dominant baryonic component of a cluster of galaxies. Right. So, and the reason why it is offset is because this cluster has been in a merger, and because the intracluster medium is collisional, when the two parts of the cluster smash into each other, the intracluster medium sort of swells and wallops about, whereas the intracluster light is just like the total mass, the dark matter mass, it's collisionless, so just passes through one another. And so they are thought to be better tracers of the total mass than, say, the X-ray emission. And so this is one of the reasons why people are really interested in intracluster light at the moment, is to use it as a cosmological tool. The other reason is to use it as a tool for understanding galaxy evolution and cluster assembly. And when I go into detail with that, showing you this image. So this is just a gallery of brightest cluster galaxies. So the central galaxy in a cluster, as observed by, I believe these is the Hubble Space Telescope images of these particular clusters. Now, the central galaxy of a cluster is a very special galaxy. It doesn't have a normal evolutionary history, and they are the most massive galaxies in the universe, which means they're actually quite easy to observe, and we can observe them all the way out to redshift 1, even 2, fairly easily. However, they are extremely hard to model correctly. And the reason is that the brightest cluster galaxies that we observe tend to grow too slowly. In this left-hand plot, I'm showing you a merger tree. A merger tree is just showing you all of the galaxies that will merge with the brightest cluster galaxy as it assembles over time. So all of these little lines are different mass galaxies, and they all merge with the brightest cluster galaxy. And all of this merging should bring in a lot of mass. So if you look at this plot on the right, which shows you the stellar mass as a function of look-back time or redshift, the mass is expected to be fairly low at high redshift and then increase over time because of all of this merging. And yet, in a really interesting Nature paper by Chris Collins in 2009, he found that really there was no growth in the brightest cluster galaxies. This really was a big problem at the time. So if we plot it on this graph, this shows you the mass ratio between the brightest cluster galaxy at some redshift, so at redshift 1, compared to what it is at redshift 0. And so the observations used to say they all lie at 1, so there's no growth. And the simulations say that it lies all the way down here with lots of growth. And then over time, actually, the observations shifted down and the simulations shifted up. Now, the observations shifted down because it became a little bit easier to measure the mass of these galaxies. But the reasons why the simulations shifted up is because instead of dumping all of the stars into the galaxy, instead, the stars were not dumped into the galaxy, but any incoming galaxy was dumped into the intracluster light. And so therefore, the intracluster light is a big test of the predictions of galaxy formation and cluster models. So these are just some predictions from one particular semi-analytic model that shows you that the amount of intracluster light should grow over time. So this is the amount of light as a function of cluster mass. And at high redshift, there's not much intracluster light. And as you go up in redshift, there's more intracluster light. And that's because instead of the stars being dumped into the galaxy, they're being dumped into the intracluster light. And so the intracluster light is a great test of these cluster assembly models and galaxy formation physics. So we need to measure this intracluster light, and this is where the Euclid Space Telescope comes in. So Euclid is an ESA mission, and it was launched just over a year ago successfully, and it's sitting at the Lagrange point 2, where it is going to be imaging the sky for the next 6 years, actually 5 years from now, because it's already spent a year observing the sky. And it's going to observe about a third of the sky, so a really significant amount. It's going to start at the galactic poles, the North and South Pole, and then it's going to observe slowly until it reaches the galactic plane. But it's not going to actually image the plane. It's just going to observe really far from the galaxy. And that's because its main mission is to observe well, it's to determine cosmological parameters, the expansion rate of the universe. And it's going to do that through two tests, weak gravitational lensing and redshift space distortions. But I'm not going to talk about those at all. What I'm going to be talking about is what we term legacy science with Euclid Space Mission. Legacy science is all of the science that can be done with this amazing survey that isn't to do with these two tests of cosmology. And one of those is the intracluster light. Now, the reason this telescope has been optimized to make sure it can take really good images of weak gravitational lensing, so it could really check the shape of a galaxy and measure that very precisely. And those requirements mean that it is an excellent intracluster light detector, because it means there's very little scattered light, and the PSF, the point source function, is very compact. So stars look extremely compact in these images. Now, most of Euclid will be a survey, so it's just going to image the whole sky. But in November, the first images Euclid took was of a handful of special sources. So you can see there are some really pretty galaxies. There's this beautiful globular cluster and some interstellar medium. And then this, which is the Perseus cluster, which I'm going to be talking about today. So the first science results came from these sets of images. And Perseus cluster, which is the focus of today, is the nearest massive cluster. It's only 72 megaparsecs away, and it is the brightest X-ray cluster in the night sky. And this here is an image of the X-ray from the intracluster medium. It's a very messy system. You can see these holes in the intracluster medium, and that's because at the center of this cluster, which is right at the center of this galaxy, which is the BCG, there is an AGN, which is shooting out jets of ionized plasma that's blowing bubbles in this intracluster medium and heating it up. So this is a cool core, so the intracluster medium is actually cooling down and then being heated up by the AGN. So we're going to take you through the images. So this is what the processed image from the Euclid telescope looks like for Perseus. And this is in the I-band image. Now this is, although it's processed, it's not quite at the good well, it's not quite good enough for our intracluster light. In order for us to do our intracluster light, we have to do some further steps. We have to remove persistence. This occurs in the near-infrared images, and it's just that when a bright light shines on a near-infrared detector and you read out the detector, not all of the charge goes. Some of it stays there. And so that's not really a big problem for most studies, but for low surface brightness stuff like intracluster light, it's a big problem. We had to remove galactic cirrus. I'm going to point out a few patches. Galactic cirrus looks like this, sort of wispy clouds that are in the image. And that just comes from the galactic cirrus in our own galaxy, and we are trying to look at the light beyond that, so we have to subtract it. And we use the WISE telescope to model the cirrus and subtract it. And finally, scattered light. You may remember I said there was very little scattered light, but you can see that there is still a gradient across this whole image, and that is from scattered light. So I won't go into details, but all of these things were removed. And so we now get a very flat image, and it allows us to explore the intracluster light around this central region. So I'm going to talk to you about two traces of the intracluster light. The first one is diffuse light. So if you look over in this patch, you can see that the background where there aren't stars is very dark black. Whereas if you look closer to the galaxy, you can see there's this kind of gray beige light. And that is your intracluster light. That's how we can pick it out at this distance. So you can't see the individual stars, but you can just see some sort of diffuse light from the millions of stars that exist there. The second tracer of intracluster light is this. Oh, I skipped ahead of one. Let me just show you. I'm going to go into just this patch and zoom in just that tiny little patch. And here you can see it. And so this is a stream of filaments from the brightest cluster galaxy, which is just above there. There's a little dwarf galaxy and some fluff, some background galaxies are here. But what I want you to notice are these dots that are all around here. These dots look like just stars. They look like just point sources in the image. However, they are in fact globular clusters at the same redshift as the cluster. So a globular cluster, this is an image of a globular cluster in our own galaxy. They are something like 10,000, 100,000 or 1,000,000 stars in a really compact configuration. And the stars are generally extremely old, typically as old as our universe is, or just less than that. And they're generally quite metal poor, the stars. So it's thought that these objects formed right at the beginning of galaxy formation, was that stars formed in these globular clusters. And we're seeing them at the redshift of Perseus, and at that redshift, they're so far away that we can no longer resolve their structure, and so we just see them as a single point of light. But these globular clusters were removed from other galaxies, just like intracluster light was. It was tidally stripped or ripped apart from galaxies as they orbit the cluster. And so they're good tracers of the intracluster light as well. And we can learn a lot from the globular cluster population, as I'll show you. So here's our first results, which is really just showing you the distribution of the globular clusters, which is on the right here, and also the intracluster light, which is on the left here. So I've just now shown you a single image band. So this is the H band, and I'm showing you all of the light. I'm not masking out any galaxies in this image. The black circle, it marks 50 kiloparsecs from the brightest cluster galaxy. So really everything within that radius should be considered the brightest cluster galaxy of the cluster. And then the white dashed ellipse shows you 300 kiloparsecs. We've fitted isophotes to the intracluster light. So basically we've fitted an elliptical model to all of the isophotes, and this is the best fit ellipse at 300 kiloparsecs. So you can sort of see within that radius, you can really see that there is intracluster light with your eyes. Beyond that, we have to do some stacking. If I then take you over to the globular clusters, this is an image which just shows you every point is just a single globular cluster, and then I've smoothed it. But what I've done first is I've masked out all of the galaxies, large galaxies and stars in this image, except for this galaxy here, which is this one here. You can see there is an excess of globular clusters here, and it kind of blends in with the brightest cluster galaxy here. And it's so difficult, it's so close that actually we have to model the globular clusters from here as well as here and then subtract these off. So that's why I'm showing them all. But hopefully you can see that when we fit an ellipse to this region, we do tend to have a similar shape. So this is again 300 kiloparsecs from the center, and you can see that there is an excess of globular clusters all the way out into the intracluster region. So these globular clusters all the way out here are sort of not associated with any particular galaxy, but are associated with the cluster as a whole. To just give you some numbers of that, we have about 1.6 billion solar masses of stars in the intracluster light, so it is really significant component. And then we have about 70,000 globular clusters in this region. So really huge amounts of stars, and it is a significant component, even though it's so diffuse that it doesn't look very bright. I'm going to talk to you a little bit about the distribution of it. I'll just go back once. So we fitted elliptical isophotes to several annuli around both the intracluster light and the globular clusters. And then in the next image, I'm showing you a comparison of their ellipticity of those ellipses and the position angle of the ellipses. And the different lines show you the blue, red, green, and black are all the different images that Euclid can observe. So there's a visible band, which is the I band, and then there's the 3 near-infrared bands. And you can see the ellipticity is very similar, and the position angle is very similar for all of those intracluster light measurements. The globular cluster distribution is kind of in this purple line, and you can see there is some offset. However, it does seem to be very, very similar in terms of the ellipticity. The position angle is different just in the center, but on larger scales, the position angle is very similar. And finally, we can see in detail, here's the light profile of the globular cluster distribution in purple. So you can see at the center, there's we're kind of incomplete because it's very hard to pick out globular clusters when you've got a very bright underlying galaxy. But then you see this profile of globular clusters. You can see globular clusters. With your eye, you were able to see it to 200 or 300 kiloparsecs, which is about there. But actually, you can see an excess of globular clusters all the way out to about 600 kiloparsecs. Now in black here, and you can see it underneath, you can see the intracluster light from the H band. So they deviate in the central region where you've got your really bright galaxy. There's much more light than there is globular clusters, but from about 60, 70 kiloparsecs onwards, then the profiles are almost identical. And so I really want to emphasize that the distribution of the intracluster light and the globular clusters are very similar. And this is going back to this idea of treating the intracluster light as a tracer of the dark matter halo, because these the intracluster light and the globular clusters are so consistent, it means that they are likely to be governed by the same gravitational potential, which means they're governed by the potential of the dark matter. And if we look at the ellipticity, we can see that it is actually about 0.4 on the large scale. So it's really highly elliptical, and that's consistent with the predictions of lambda CDM for a dark matter halo. And that is actually much more elliptical than the X-rays. Here is the ellipticity of the X-rays at 2 points, and you can see it's much more circular than the intracluster light. And that's because the intercluster light, sorry, the intercluster medium, the X-rays from the intercluster medium, they're collisional, and so they tend to become spherical in shape as opposed to the ICL. Another thing that's quite obvious from these images, and you probably have noticed it already, is that the brightest cluster galaxy is centered here. Whereas if you look at the intracluster light on large scales, you can see that it seems to be centered slightly offset from the brightest cluster galaxy. And that's about a 60 kiloparsec offset in this distance. I'm just updating. So the image I've just changed a little bit. So now in the pink contours show you the globular cluster distribution. So you can see the globular clusters are also extended in this direction. So the centroid of the globular clusters is very similar to the centroid of the intracluster light. But the X-rays, which are shown in these blue contours, first of all, you can see the difference in terms of the shape, the ellipticity. They are far more circular than the intracluster light. But you can also see that the X-rays tend to be shifted to this direction. If we just look at this contour, not the outermost one, but the one before that, see it goes all the way around here. It tends to be shifted in this direction. From this distance to there and from this to there, you can see it's actually shifted about 60 kiloparsecs to the east. And so we're having this very different situation in which the intracluster light seems to be centered here. The X-rays seem to be centered all the way over here, whereas the brightest cluster galaxy is centered in the middle. And this is really confusing because offsets between the brightest cluster galaxy and the intracluster light or the X-ray light should only happen if a cluster is merging. And yet Perseus is really the archetypical relaxed cluster with a very strong cooling flow. It's thought that it has been relaxed for many gigayears. So we didn't expect such a strong disagreement between all of these traces. And so this is pointing out that actually what we might expect as being relaxed clusters may not be, and the intracluster light may be able to tell us that using Euclid images. I'm going to move on to talk a little bit about where the intracluster light comes from, because this, as we heard, it's really important that the intracluster light can tell us about galaxy formation models, but to do that, we have to figure out how much of it there is and where this light comes from, which particular galaxies form the intracluster light. And Euclid has provided 3 new measurements that we haven't been able to find before. So the first one is near-infrared colors. Then we are going to talk about globular cluster luminosity functions and the specific frequency. Now, the reason why near-infrared colors are so special is because they don't have a strong age metallicity degeneracy. So here is the near-infrared color, the Y minus J color, and you can see for different metallicities, which are the different colored lines, they're almost straight. So it almost doesn't matter what the age of the stellar population is. It really is the metallicity has exactly the same color regardless of the age. There's a little bit more trend for the J minus H and the I minus J colors, but generally we have it's very straight, so there's very little degeneracy as long as the stellar population is older than 2 gigayears, and that is usually okay because intracluster light is generally quite old. The reason why we haven't been able to do this until Euclid is because near infrared, the sky in the near infrared is infinitely bright. So it's very hard to measure intracluster light from the ground. And in space telescopes like James Webb or HST, the infrared detectors are so small that you can't actually measure much of the light. So this really is a very new observation that we've done. And so here we're showing the Y minus J colors and the J minus H colors of the intracluster light over here as a function of radius from the center of the cluster. And so in the center, we've hatched this out because this is a very complex brightest cluster galaxy, and we don't quite trust the colors right at the center. But beyond the center, we can see that the color decreases and then it seems to flatten out. And the color decreases from what is sort of solar metallicity down to being subsolar metallicity. So this negative color gradient, this suggests that we have more metal poor stars in the outskirts of the galaxy and more metal poor stars in the intracluster light region. Now, this metallicity is consistent with sort of intermediate mass galaxies, so something like 10 to the 10 solar mass galaxies. So this is our first clue as to where the intracluster light comes from. The next clues we have come from the globular clusters, but I just want to go over how we selected the globular clusters in this image. So the globular clusters are only really visible in the I band from Euclid. You can compare it to an I band from the ground, and you can just see how much better the resolution is from Euclid. And the fact that you've got this high resolution in Euclid means that you really can detect these globular clusters. Unfortunately, in the near infrared bands, your pixel sizes are much, much larger. And so therefore, your resolution isn't as high. And so it means you're not able to select your globular clusters in your near infrared images. So we're not able to select globular clusters using colors. Instead, all we do is we have this compact criteria. So we say it has to be very compact, like a point source. And then what we do is we statistically subtract the background. So here I'm showing you the globular cluster luminosity function. Well, no, sorry, it's not globular. I'm showing you the luminosity function of all sources very close to the brightest cluster galaxy, and then further away, and further away. So this is all sources that are compact. And then in gray down here, you can see the luminosity function of sources that are really far in the outskirts of the image. So more than 600 kiloparsecs away. And so this is the luminosity function of, say, stars and background galaxies and contaminants to our population. And we simply take this luminosity function and we subtract this one, and this luminosity function, and subtract this one to reveal the luminosity function of our globular clusters. And so here we have the results. So this is the luminosity function of the globular clusters quite close to the center of the galaxy, the brightest cluster galaxy. So 20 to 40 kiloparsecs, most people would argue that really is within the cluster, within the galaxy. Now, it's well known that from empirical measurements that the luminosity function of globular clusters has this Gaussian shape. And it's also well known that there's a well-defined peak, which in Perseus would occur at 26.3 magnitudes. And the standard deviation of this Gaussian would be about 1.4 magnitudes. And so we fit this curve. We actually stop here with our fit, and we just fit these data points because at this point we're incomplete. We don't have, and the data don't go deep enough to cover this. And here is our fit, the mean and the standard deviation of a Gaussian. And you can see they are exactly the same as this within our uncertainties. So this proves that our method is working. And now I'd like to show you for the first time what the globular cluster luminosity function looks like in the intracluster region. So this hasn't been done before, and it's because it's only with Euclid's massive images that we were really able to pick out the globular clusters at such a large distance. So in yellow, we have the annulus, which is in between 40 and 100 kiloparsecs, so sort of the outskirts of the brightest cluster galaxy. And then you really have the far intracluster region, so 100 to 200 kiloparsecs, 200 to 500 kiloparsecs here. Now, I tried to fit these with a Gaussian, but it wouldn't work. And so I fixed the centroid to be the same mean as for the red histogram up there, the red curve. And then I was able to fit a Gaussian, and it seems that the sigma decreases as you go further out. But I could also show you that these are pretty bad fits. So it seems that a single Gaussian is not a very good fit to the globular clusters of the intracluster region. I've got the reduced chi-squared here, which it's a bit hard to interpret, but basically it rules out these fits with more than 99.9% confidence over here. So they really are bad fits. So that means that the globular clusters don't come from massive galaxies. What I then tried to do is I tried to fit them with two Gaussians. One, which is a massive galaxy Gaussian, so one that's like the red curve, but then the other, which has dwarf galaxies. So dwarf galaxies also have a Gaussian luminosity function, but the mean is slightly shifted and the dispersion is slightly lower. And when I fit it with two Gaussians, you can see I get a much better fit. That's not surprising because I'm fitting the data with two Gaussians rather than one. So I'm always going to get a better fit. But they do seem to agree very well. And from this, you can then see that what this implies is that the luminosity function implies that there's a mixed population. There are a significant amount of globular clusters that come from dwarf galaxies. And you can see the fraction over here. So in the outermost region, about half of the globular clusters appear to come from dwarf galaxies, whereas in the inner region, more than 3/4 would come from massive galaxies and only 1/4 from the dwarf galaxies. Right, so that's given us another clue. That's told us something about that dwarf galaxies must contribute to the intracluster light. But let's talk about the specific frequency of globular clusters. What does this mean? The specific frequency tells you how many globular clusters you would expect in a galaxy or an intracluster light per unit solar mass of stars, diffuse stars. And the measure I'm using is the number of globular clusters per 10 to the 9 solar masses of stellar mass, right? So if this was 1, then you would expect 1 globular cluster in a 10 to 9 solar mass galaxy. And this is what we find going from the inner region. So this is 10 kiloparsecs, 100 kiloparsecs, and then all the way out to 600 kiloparsecs from the center of the cluster to the outskirts. And you can see that the number of globular clusters per unit mass increases as you go further out until you then saturate at about sort of 60 globular clusters per 10 to the 9 solar masses. Now this value down here, about 10, this is similar to other massive galaxies like brightest cluster galaxies. So this is consistent with what we're finding here. And actually this part is well known. This value for the specific frequency is so high that it's only ever seen in dwarf galaxies of mass less than 10 to the 9 solar masses. There is no massive galaxy that can produce this high a specific frequency. They tend to have all been destroyed. So this part, seeing the increase in the specific frequency in the outskirts of galaxies, has been discovered before by HST, but this part where we see this sort of extremely high level of globular clusters throughout the intracluster region is really new for Euclid. And it's one of the big results from this paper that we're seeing. So let's summarize what we found. We've got three key pieces of evidence. We found the ICL has subsolar metallicity, and that suggests the progenitors are about 10 to the 10 solar masses. We then found a very high specific frequency of globular clusters, and this suggests that the progenitors actually have to be even lower mass, dwarf type galaxies. And then the globular cluster luminosity function gives us an even more complex story in which they're saying actually you need a mix of galaxies to form the intracluster light, where in the center you've got the massive galaxies forming it, and in the outskirts you've got the lower mass galaxies forming it. So although this is quite complicated, it does tend to tell us that the progenitors are sort of lower mass galaxies. So it may surprise you to know that actually every single simulation that's ever been run tells us that the progenitors of intracluster light comes from massive galaxies. And there's a good reason for this. There's just not enough dwarf galaxies are expected to fall into a cluster to account for all the intracluster stars, all the globular clusters. If you count up all of those galaxies, they would have merged into bigger galaxies before they fell into the cluster. So from our hierarchical formation, they shouldn't exist. It's also, this luminosity function business in which we have the lower mass galaxies are sort of contributing more at larger radii. It's actually impossible to do that in terms of tidal stripping, because the tidal radius of a dwarf galaxy is really small. You'd have to get the galaxy, the dwarf galaxy, very close, within 100 kiloparsecs of the cluster center, in order for it to be tidally stripped. And so we would actually expect the opposite to be the case, that you would get more dwarf galaxies stripped in the core. And so we've got this disconnect between massive galaxies, the simulations and the observations. And what we need to do is to not just rely on one cluster. So we've only been relying on Perseus. And what I'm going to do is I'm just going to skip a couple of slides because I've just noticed the time and I don't want to overrun. I'm going to talk to you a little bit just for the last couple of minutes about how well we can measure intracluster light with Euclid going forward, because what we need now is not a sample of just a handful of clusters in which to measure these parameters, but we need thousands of them. And so with my postdoc, Callum Bellhouse, we've been trying to figure out a forecast how well we can detect the ICL with Euclid. So Callum's been producing images of ICL in clusters. We took a simple Circic model of the ICL, and then we added on a brightest cluster galaxy, and then we added on galaxies, satellite galaxies for this cluster. We then take our simulated cluster and we attach it to a mock image of the Euclid telescope. So here you've got galaxies and stars that are expected to be observed as they would through the Euclid telescope. You could take this cluster and you could redshift it to redshift 0.3, or you could then send it back even further, 0.6, 0.9, all the way up to redshift 1.8. And this allows us to then determine how well we can detect this intracluster light. And that's what we're showing on the left-hand plot here. Our figure of merit is the signal to noise we measure within a 50 to 200 kiloparsec aperture, this annulus around the BCG. And what we found is that as long as the cluster is at relatively low redshift, below redshift 0.5, we should detect it with a signal to noise of more than 20. So almost all of these clusters, down to the lowest mass cluster, maybe not up to sort of group scales, we should detect fairly robustly. This is then not a very strong function of stellar mass, but it is a very strong function of redshift, and the signal to noise decreases due to cosmological dimming. However, we should be able to detect a fair number of clusters at redshift 1.5 and above to a signal to noise of 3 to 5. So not at a very high signal to noise, but we should be able to detect it in this parameter space over here. Now, this image is actually slightly deceiving because even though it seems that we can detect low mass clusters, in reality, the realistic detection methods, the state-of-the-art detection methods, have really struggled with low mass clusters. So when we were counting the number of clusters we will observe, which is in this plot, we don't count anything below 10 to the 14.2. So we're only counting quite massive clusters. And here is our prediction, our forecasting for how many we should observe. Over the whole of space between redshift 0.3 and 1.8, we expect to detect about 80,000 clusters. About half of those will be between redshift 0.3 and 0.75. So we can do very good studies of the color of the intracluster light and its distribution for these clusters. But we do get a couple of thousand clusters at very high redshift that we'll be able to detect with Euclid. So to summarize, I hope I've shown you that intracluster light is a fantastic tool for understanding hierarchical galaxy formation, and we do hope to use it as a tracer of dark matter with the Euclid telescope. Euclid's early release observation of Perseus has revealed quite a few surprises. We didn't expect to have such a strong offset of the intracluster light and globular clusters from the BCG. And really the infrared colors, the luminosity function and specific frequency of the globular clusters, they seem to suggest a large fraction of the stars formed in sort of dwarf galaxies. And yet this is a contradiction to the simulation. So we're not quite sure what's going on there. However, I would warn you, I didn't quite get around to talking about this, but actually observations of high redshift clusters don't match the simulations either. So there might be something wrong with our simulations of intracluster light. And then the future is very bright because Euclid will detect at least 80,000 clusters at lots of redshift, all the way to high redshifts. And so we'll be able to do many of these studies in the future. So thank you very much.
Thanks, Nina. Do we have questions from the audience? And from Zoom? I saw that there are many questions in the Google Doc. Nobody would like to? Okay, I'm gonna read them out loud. Just a second. Questions from the
Anna, I can't hear you.
Oh, questions from Zoom?
Yeah.
Okay, so just a sec. So there's 8 questions, but nobody wants to ask them, so I'll have to do it myself. So first one, you showed 2 works from spectroscopy that don't match with yours at low Z. How sure are you where the mismatch comes from? I
don't
understand this question. Okay, next one. In the Kelly comparison, there's an excess of more massive objects. What are those? Okay.
I don't think this is mine.
No. Okay. That's right. We forgot to remove them. Or- So how did you separate the GCs from other point sources in the field of view of Perseus? That's my
Yes.
question.
Okay, so this was really difficult, and that's kind of why I tried to have this plot. Sorry, I'm going all the way back. Why I tried to have this plot in, because whoever's come up with that question is completely right. These are what I would say globular cluster candidates. The only thing we did was we detected them in the I band. And because we couldn't get any colors, we just said, right, they have to be compact. So they had to have a full width half maximum of less than like 4 pixels or something like that. We did some cut in brightness as well. So we know that they're not going to be extremely luminous, sort of 20th magnitude. So we cut that. But we still have a huge number of contaminants. Any foreground stars that are fairly dim or background galaxies that look point-like will be in there. And so we couldn't remove those out. I would love to get spectra of these, but it would be impossible for there are sort of over 70,000 of these. So you would have to have it would be very hard to get spectra of all of them. So the only way we could do it was to do a statistical subtraction. So this is where you measure the luminosity function of the background, and then you just subtract it from the luminosity function of other regions. And we did the same with the specific frequency. We counted how many objects there were in a specific place, and then we measured our background and we just subtracted that, and that gives us a number. But we can't say for definite whether one thing was a globular cluster or not. We can only tell these things statistically.
Great. And did you not use colors? The other Euclid.
No, but we didn't, because this one looks like it's there, but actually I think that one's a background galaxy sitting there rather than it being a globular cluster. But most of the globular clusters are far fainter than this, and they're just not visible in the near infrared bands. The near infrared colors are only possible for something much closer like Fornax. So I think there was a paper on the Fornax cluster with with Euclid, and they were able to measure colors, but that's much closer. So and they could even resolve them, but otherwise we couldn't use them.
So another question. How do you know the GCs are not bound to the galaxies?
Um, how do I know they're not bound to the galaxy? It's a good question. Um, they're just so far removed. I think it's so the globular clusters that are within, maybe if I find an image of them. So the globular clusters that are within this region, or within 100 kiloparsecs, I say they could be bound to the brightest cluster galaxy. But the globular clusters out here, I don't think that they could be. And I can't give you a good reason for that now. I'm sure it's got something to do with their energetics. But I guess we would need spectroscopy to confirm that.
Couldn't they be bound to low surface brightness dwarfs that we don't see at this distance?
Okay, so yes, I did do this test, and there are still so there is a small fraction, something like 10-15% could be low surface brightness dwarfs that are below the detection limit of our catalogue. But actually, we do very well at detecting all of the dwarfs, or most of the dwarfs in this region. However, in dwarfs, you typically only get a handful, or one or two, or up to a handful of globular clusters. You don't get that many, and there are just simply too many in this whole field. It would have to be that the whole region is covered by dwarf galaxies for you to get that many globular clusters.
Cool. More questions? If people want to ask in Zoom, just shout out. I'm gonna make two more that are here. How complete are you in the I band?
For globular clusters or intracluster light?
For both.
For both. So let's start with the intracluster light. The intracluster light is actually not determined by the depth of the images. So statistically, the image depth is about 29th magnitude per square arc second, averaged over 100 square arc second region. So that's really deep, not as deep as, say, some of the 10-year depth of LSST, but really deep. However, what limits the background measurement, and the background measurement is completely dominated by galactic cirrus, which entirely covers this region. So we really can't go much fainter than the cirrus. That's what's limiting us. For the globular clusters, I can actually read that off. Let me read that off. There we go. So the globular cluster luminosity function, we are about 26.2 magnitudes. That's our limiting magnitude for point sources. And that's fairly well defined. The only region where we're actually less complete is in the central region of galaxies. So when you've got a really bright galaxy, it's much harder to select globular clusters. And this is why we're less complete up here for the inner regions. And if I was to take the central region, the completeness would drop off far more rapidly.
And regarding this, do you do photometry yourselves for the globulars? Do you actually remove the central parts of the galaxies, or you perform photometry there, or it comes out of the pipeline of the survey?
No, we do photometry ourselves. It will not be in the main survey. Well, this is a really complex question because the survey and what is going to be given in the survey catalogues is constantly changing. And so they haven't really agreed on what they're going to provide. But as far as I know, things like sources within a galaxy, such as the globular clusters very close to another galaxy, won't be in the catalogue. So you have to get the images yourself and do your own post-processing of the images to get the globular clusters.
It's not a last question. It's known that NGC 1275 has many young clusters. Did you remove them, the point source young clusters from your analysis?
Let me just ask that question again. Did you say about the young globular clusters?
In NGC 1275, they have that
Yes.
beautiful spider structure. I don't know what it is.
It's so NGC7. I don't know if I have a good image of it, but yes, let's just go here. Actually, that's not true. I have a much better image of it. There we go. So NGC 1275 is my favorite galaxy in the entire universe. Literally, I did my PhD on this galaxy, and it has these streams of ionized gas that are being dragged out of the brightest cluster galaxy. And so you can kind of see this ionized gas here. And from this gas, you get these streams of very young globular clusters that are being formed from this. Now, some of the ionized gas doesn't form these clusters, but some of them does. And in answer to your question, we removed the entire of the nebula and all of these, all of the globular clusters associated with that nebula. However, there is some evidence that maybe this has been happening for quite some time, and so therefore the globular clusters may not be associated with any nebulous emission, and those we were not able to remove because they would just be within our compactness criteria, and because they don't have any indication that they're young, we wouldn't be able to remove them. So those ones are in there, but the vast majority of the very young ones have been removed.
More questions?
My question is, so you see also intracluster gas. So how you can separate the gas from, the diffuse light? Is it very obvious that you can separate, or you have filters? I don't know. How can you separate the emitting gas from the diffuse light that's more stars and clusters?
Yeah. So we were very lucky with Perseus. We had a H-alpha image of this cluster as well. So we were able to identify the regions where this ionized gas was and mask it. But you bring up a really good question, because what are we going to do for all of the clusters, the 80,000 clusters we're going to detect with Euclid, for which we won't have H-alpha imaging? The only thing I can say is that really, apart from in Perseus, most of the time this ionized gas is constrained to lie within about 50 kiloparsecs. Even in Perseus, I think it only gets out to about 60 kiloparsecs. So as long as you're able to remove the central region around the BCG, then you're probably fairly safe that the surrounding stuff is actually intracluster light rather than ionized gas.
Thank you.
I have many other questions, but then I think I'll email you. Otherwise, I was taking up all the time. But to finalize, a last question. What are the prospects for this kind of work for intracluster light, combining the LSST catalogs with the future catalogs with Euclid ones, at least for the clusters in the south?
Okay, so it's good. The prospects are very good, but something to note is that actually, because LSST has been delayed by a bit, everybody will actually receive the images of Euclid before LSST. So the first data release of Euclid is going to be in about a year and a half from now, I believe. So March 2026. I think, is the DR1. And so by that time, I think LSST will just be getting going. And so they won't have the full depth. And so we're whereas we had hoped we would be working together, it now looks like we'll be able to do stuff with Euclid first, and then once the depth of LSST builds up, we'd be able to examine the same clusters in the optical. And that would be very exciting because we can get much more color, many more colors of the light. I've said that the near-infrared colors are enough to do sort of some very basic metallicity models. But if we wanted to go even further and really do some stellar population modeling of it, we would need multiple colors. And that's where LSST comes in. Also, LSST will go about a magnitude deeper. Well, it's predicted to go a magnitude deeper than Euclid will. So you have that trade-off that you'll get the high resolution with Euclid, but you'll actually get it deeper with LSST.
Thanks a lot. So if there are no more questions, let's thank Nina again for the nice demonstration. Great to have you here. Bye-bye.
Thank you. Bye.